Welcome back to Math Class.
Math Class. That's enough of that.
What up, people? We're going to talk about parallel lines today. And we're going to start off with an example, but again, just changing the color here. So, let's suppose that Kira can run at 5 meters a second, and she's going to race against Desiree.
No.
Desiree also gets a head start. If Desiree can also run at 5 meters per second, will Kira ever catch her? Explain. No, she will not. Why the heck not, you say? Well, because if they're running at the same speed, but they start at different points, then the distance between them will be constant. So at the same speed. The distance between them is constant.
Okay, so how about if Desiree can only run at 3 meters per second? Will Kira ever catch her in that case? Then, yes.
Yep.
The distance between them will shrink until they meet. So the answer is yes. Okay. When the rates of change are identical, then the starting points differ, like in the first example, then no intersection will happen. And if they're different, an intersection will occur, like in the second example. So, Mr. Thide is going to define parallel lines.
Oh, you know it. But I'll do so in, lilac?
Ooh.
Yeah, it's a nice color. I like this font size. So parallel lines have lines that have... Oh, no. I'm a failure. No, nailed it.
Cross it out, Mr. Thide.
Never. What, the T? Do. I don't know if I had started a sentence or not. That sentence ended. Parallel lines. They have different points, but the same slope.
So, if we take a look at this example, we have line 1, and line 1 contains the following points: 10, 3, and 5, 10. Line 2 is then parallel to line 1, so we got to find the slope of line 2. Well, first of all, let's find the slope of line 1. Okay, we first are going to just label our points. We've got the x1, y1, and the x2, y2. And from the last lesson, we know that the slope is just the difference in the y value. So our change in y, which is our y2 minus y1, over our change in x, which is our x2 minus x1. When we plug in these values, we get 10 minus 3 over 5 minus 10. And if we go ahead and do that, 10 minus 3 is 7, and 5 minus 10 is negative 5. And so we get the slope of negative 7/5. Well, if we know that line 2 is parallel to line 1, then we know that they must have the same slope from the example/definition above. So slope of line 2 must also be negative 7/5. Whoop, whoop, 7/5.
Okay, next example. So we have 3 lines in this case where we have points on each of the lines. So we want to figure out which ones are parallel, and remember that the definition of them being parallel means that they will have the same slope. So we want to figure out each of their slopes, and then we want to compare them. So I am going to use M1, M2, and M3 to designate line 1, line 2, and line 3. So we're going to do some plugging in here. Okay, I'm not going to write out the whole formula each time. because we don't have that much space. But we're still doing y2 minus y1 over x2 minus x1 in each case. Label your points if you would like. So we have some x1, y1, x2, y2 action a few times. Okay, so we get 4 minus 6 over 8 minus 4. Okay, and then of course we always want to reduce. So we're going to get a negative 2 over 4, which gives us negative 1/2. I'm actually going to change colors so you guys can see which lines I'm working on each time. Okay, next set of points. x1, y1, x2, y2. So, slope 2. Okay, we have negative 1 minus negative 3, pardon me, over negative 7. Minus, there we go, negative 10, which gives us 2 over 3. Then for the third line, again, I'm just going to pick another color to keep it clear here. We're going to try and label this here, x1, y1, x2, y2. Slope 3. So we have 9 minus 5 over, what do we have here? Negative 8 minus 0. And that gives us 4 over negative 8, which reduces again to negative 1/2. So then we just need to compare the three slopes to figure out which ones are the same. And so because we can see that this is negative 1/2, and so is the last one, then lines 1 and, oh, that's not an and 3 are parallel. We can also write line 1 is parallel to line 3. That symbol means parallel.
It looks like the two L's in parallel.
Whoa! It does.
That's pretty wicked.
It's almost if it was intentional.
Whoa! This example involves a parallelogram. What's a parallelogram? He asked his colleagues to no response. Anyways.
I thought you were asking the kids.
No, I was asking you two. Directly looked at the two of you too.
I thought you thought
Prompted for a response.
You did not look at me. You knew not to look at me.
Yeah, no, I only looked at the math department.
Yeah.
All right, parallelogram. You might note that it has the word parallel in its name. So it's got two sets of parallel sides. So that's what we need to establish. As long as this has two sets of parallel sides, it must be parallelogram. So we'll find all these slopes. We'll find the slope of segment AB. We will also find the slope of segment BC. We'll find the slope of segment CD and the slope of, well, from D to A, but I prefer to write things alphabetically, so AD. Not to be confused with the number 80. You should pause the video and find the slopes of all these things to make sure you can do it, because I'm about to do it right now. Neat. It's real quiet in here today. Oh, look at this. Ooh, let's pick a highlighter color. This could be interesting. This slope is same as this slope. And this slope is same as this slope. We can then draw a conclusion as follows. Whatever this quadrilateral is, ABCD has two pairs of parallel sides. So therefore, it's a parallelogram. All right, who wants to tackle the last example?
Ooh! Not me. Just kidding. All right. So if we are given the points P, Q, R, and S, we want to prove that the quadrilateral is actually a rhombus. Any clue what a a rhombus is?
Learn your shapes.
Hello? Anyone there? Hello? All right. So a rhombus is just a parallelogram, but the thing that makes it a rhombus is the fact that it has 4 equal side lengths. So, for example, a square is a parallelogram because all of the sides are equal, and the 2 pairs of lines, 2 pairs of opposite sides are parallel. So first, we're going to make sure that we have 2 sets of parallel lines. So just as Mr. Athai did in the question above, we gonna pick a pretty color. What you feeling? So many options. I'm gonna go, this like dusty blue color. All right, so we're gonna do the same thing as above. So we're gonna take the slope of PQ. Then we're gonna take the slope of RS and the slope of QR and the slope of PS. And if we take a peek ski at all of these, we can actually figure out all of the slopes. And you know how to do that already. So if you wouldn't mind, if you could please just calculate the slopes on your own and then double check you actually know how to do it. Seriously, pause the video. Do it now.
I don't think they did.
Did you pause the video? Because you could probably still hear me. All right, I've waited long enough. So, if we are going to go ahead and calculate the slopes, just double check that your answers match mine. Ooh, come on, line. Here we go. 5 plus 2. And that reduces to -1 over 7. And here we get -2 plus 3. And that reduces to -1 over 7. Look! We've got some parallel slopes. Or parallel lines, because their slopes are the same. Check out these guys. Oh. And that gives me -7 over 1, which is just -7. I don't need to write the 1. I don't want that E1 error up in here. And then... No way! Another one. What the heck? So we know for sure it's a parallelogram. That is not in question here. And you know what? I'm a big fan of putting boxes around my final little work pieces here. So I'm just going to do it. I know Mrs. Friesen and Mr. Athai don't always, but
Wow. Wow.
I just like the boxes, you know? Now, what we have to do next is we have to make sure that the distances are equal. We could go ahead and find the distance of every single line segment, and that seems fine and all, but what we could also do is as long as 2 opposite sides, 2 adjacent sides are equal in length, then we could assume that the other ones are as well because of our parallel slopes. So we are going to go ahead and find the distance of PQ. And you actually know how to find this distance like what we did in the last unit, right? We had our distance was like the hypotenuse of a right angle triangle, right? Which is our change in our x's squared plus our change in our y's squared. And we can go ahead and find that 7 squared and negative 1 squared, which gives us 49. Plus 1, which gives us 50. And of course, our d of PQ was squared all this time. And to get that d squared to be just a d, we got to square root the both sides, you know? And if we've done that, we should get d, or the distance of PQ, is the root of 50. And again, a big fan of boxes. Now, we could also find the distance of side length QR. And if you didn't pause the video that first time, if you could do that now and just make sure you really know your distance calculations, that would be wicked.
Really, even if you did pause it the first time, you should still pause it now. Give it a try yourself, right?
Yeah, you're independent. And just in case you aren't, here we go. So we have the change in x's squared and the change in y squared. And we could carry this down. And 1 squared is 1, negative 7 squared is 49. So we get 50. We got to square root both sides because that's how we isolate. Ooh, whoa, whoa. I forgot the little exponent there. Oops. But as we square root both sides, we end up with a distance of root 50. And wouldn't you know? There we go. 2 distances that are equal. So now we've got 2 sets of parallel sides and the adjacent sides are the same length. Why don't we write that in a sentence, hey? So PQRS has 2 sets of parallel sides. And the adjacent sides are the same length.
Sick.
Right. Therefore, my my PQRS is a rhombus. All right, that's all. If you could please just go ahead and give this homework a try, that would be the best. Yeah, anything to add?
Something about teams?
Oh, go team!
And look on your Microsoft Teams.
Oh yeah, also go do that.
Go, teams.